Hey guys, and today I'm going to talk to you about the fourth installment of chemistry, and we're going to talk specifically about chemical reactions. Now, you're encouraged to follow along using the guided notes that are provided on this presentation, and the PowerPoint is also available, and it features various links that can be used to extend the information provided. So let's go ahead and get started. So here's our textbook reference resource as we talk about chemical reactions. And one thing that you should notice is that there are several links available for the various topics, and it's there to kind of extend the information that I provide as I go through each series of pieces of information. Now again, you're encouraged to use the guided notes because it kind of focuses on the vocab and some of the other various tidbits regarding these topics. And you're also welcome to actually use the OpenStax website, which is a wonderful tool as a textbook and free as you pursue understanding the information provided here today. Now, I want to begin by extending our information on formula mass and connect it to a concept called the mole concept. And before we connect the dots to the actual mole concept, let's go ahead and reiterate some of the things we might have discussed prior. First thing is that of the formula mass, which refers to the substance sum of average atomic masses. And you can acquire this value mathematically. You've heard me term it molar mass, and the concept still holds true. Now we're looking at something called the molecular mass, which is the same thing from a value standpoint. And to do that, you always will need a periodic table. Periodic table will be useful in obtaining source information that you'll use to calculate the molecular mass. The other thing you'll need to be able to recognize is the feature of something called subscripts, which was addressed in a previous presentation. And subscripts are just the numbers that indicate the quantity of elements involved in that particular compound. For instance, in this particular cited example, we have a chemical formula that is CHCl with a 3, which is carbon, hydrogen, and chlorine. Well, there's one atom of carbon, one atom of hydrogen, and it's understood to be 3 atoms of chlorine. And so you take those quantities, and then you're going to multiply the number of those quantities by the individual elements' respective average atomic mass. Now, you've heard the term average atomic mass used to refer to the number, the mass number, or the atomic mass, which is the larger number of the element found on the periodic table. And using that value, you multiply the quantity and the average atomic mass, and it gives you a subtotal, which you then proceed with doing addition to find the sum total of all 3 values. And so in this particular instance, the molecular mass of this compound is 11937. And that's the molecular mass. Now, to reiterate that, you definitely need a periodic table to do this. You can't determine the molecular mass without having a periodic table available to you. The other thing you want to recognize is the subscripts, which indicates the quantity involved. One thing to note is if there is no necessarily number next to the element, it means that there's just one of those. And so in this case, like I said, we have 1 carbon, 1 hydrogen, and 3 chlorine atoms. And then you take the sum of the multiplication product of the quantity and the average atomic mass. So when you're looking at this idea of molecular mass, one of the things that needs to come out is an understanding that the approach is relatively the same to find that number, but the terminology is slightly different. Sometimes you might see in the text where it refers to something called the formula mass. The formula mass is synonymous in the sense that you're calculating the same value, but it's not the same terminology. The molecular mass refers to your compounds when they are covalent in nature, and in this case, when we're talking about ionic compounds, we're talking about our formula mass. So depending on the nature of the question, it might ask you about for the formula mass or the molecular mass, it might ask for the molar weight or the molar mass. The information that you're obtaining from a value standpoint is going to be the same, but the only difference is going to be in the terminology. So in this case, we're tasked with finding the formula mass of sodium chloride, which is represented by the chemical formula NaCl. And so because it's NaCl, we know that we have 1 atom of Na and 1 atom of Cl. We're going to represent each of those quantities by their respective average atomic mass, which is the number you can obtain using the periodic table. It's the larger number found underneath each of these elements. So for sodium, it's 22.99. I might average it to 23 if you want to. And then for chlorine, it's 35.45. And so you just take the sum of those two and you get a formula mass of 58.44, which essentially is reminiscent of obtaining the molecular mass when you have the other type of compound. Now, whether you're finding the formula mass or the molecular mass, all of those values are going to be pertinent when we tie it into this concept called a mole. Now, a mole, as was evidenced and indicated in the first presentation, refers to the SI unit for the amount of a substance. So they quantify the unit of substance by something called the mole. And you want to think of it in the context of thinking of it like maybe a pair or a dozen. When you think of a pair of something, you're thinking obviously of two. It doesn't matter how big that thing is or how small it is, but a pair is two. When you think of a dozen, you're always thinking of quantity of it being 12. So it doesn't matter how large, how small it is, but it is 12. So a mole has a specific number of or a quantity of those particular units. And those units define what a mole is. And so when we're talking about chemistry, that is our unified concept that we use to approach understanding the mole. And those units are 6.02214,179 times 10 raised to the 23rd molecules. And so that's what 1 mole is equal to. And a lot of times we approximate that value to equaling 6.022 or 6.02 times 10 to the 23rd. And this refers to units, molecules, atoms, ions. It can be any type of unit, but it constitutes a mole. And that is from something called Avogadro's number. And Avogadro number was discovered by Mr. Avogadro, Amadeus Avogadro, and it is a constant. And it is used to connect 1 mole of any substance. Now, here's the thing. When you think of the context of that number, Avogadro's number, when you apply that many units of any of those atoms, they all are going to have a characteristic weight or mass, if you will. And that mass is going to be unique to the element or compound in question. So let's look at an example of Avogadro's number quantities of each of these respective elements. In this illustration, we have zinc, carbon, magnesium, copper, sulfur, silicon, lead, and tin. And in each of these cases, all of them represent 1 mole of substance. Essentially, each one of these represents 6.022 times 10 to the 23rd atoms of each of those elements. And what you'll notice is that each compound, while they each represent 1 mole of substance, they have a different actual amount of substance present. Meaning, it's 1 mole, but maybe there's a count of 6.022 times 10 to the 23rd atoms. And because some atoms are larger than others, the amount of represented compound is different. If you look at the example where it says 12 grams of carbon, or 12 GC, 12 grams of carbon, the amount of that is uniquely different from that of the compound indicated by 118.7 grams SN, which is 118.7 grams of tin. And that's because 1 mole is going to vary from substance to substance. It's just like if you were comparing the weight of 12 cars versus 12 tanks. 12 cars is still 12. 12 tanks is still 12. However, if you were to put each of them on a scale, obviously their sum total on mass would be substantially different. And that's what this illustration denotes. So, when we're talking about molecular mass and we're talking about formula mass, the term molar mass should come up. The molar mass of an element or compound is the mass in grams of 1 mole of that substance. It's a property expressed in units of grams per mole. And so you can find the molar mass of any substance using your mass number, or they would say the atomic or formula mass in AMU. So it's a very approachable subject, and it's been approached prior, but the molar mass is essentially synonymous with your formula mass and your atomic mass and atomic weight, your formula weight, all of those compounds. The verbiage is what's slightly different. And so let's extend this concept of molar mass of elements. Here you have examples of your carbon, your hydrogen, your oxygen, sodium, and chlorine, and each of them have a featured average atomic mass, and each of them have a featured molar mass. And conveniently, the number is the same amongst the two of them. And so when you're talking about these values, you want to understand that that is essentially the same concept. And we've also established what a mole is. Well, now that we know what a mole is, we need to also talk about the relationship between the mole, grams, and atoms. And one of the popular graphic representations of that denotes how you can go between these units, because that is a calculating concept that you want to be able to do. Now, the relationship between moles and atoms is Avogadro's number, which we approached, 6.02 times 10 to the 23rd. However, one of the concepts we're going to have to extend is our understanding of connecting the idea of this mole concept to the number of grams. And depending on the approach that you're using, you're going to either multiply or divide by the compound in question's molar mass. And that's the value we've already looked at. So using Avogadro's number, you can connect the relationship between moles and atoms. And using the compound's atomic or molar mass, you can connect the concepts of moles to grams. And like I mentioned in previous presentations, the click here option in the presentation is a wonderful resource to look at additional examples of how to calculate between moles and grams moles, and moles atoms. So please take advantage of that as a resource, especially if you feel that the presentation on this needs to be a little bit more extensive. So let's talk about some cited examples. Here we have a question that tasked us with using our 4.7 grams of material, and it wants us to find the moles. And so according to this question, it's saying, well, the estimated average requirement for dietary potassium is 4.7 grams, and it'd like to know what that value is in moles. Well, according to the diagram that we previously looked at, if you're going from moles to grams or grams to moles, is what it's going to tell you or dictate the approach that you're going to use. Now, if we're looking at the question, we're given grams and we're being tasked with finding moles. And if we're following that of the diagram where we're looking at grams and we're going to moles, according to the diagram provided, we are taking the grams of 4.7 and we're going to divide that by the atomic or molar mass to get our moles. And what does it indicate in this particular slide? Well, it tells us that we're going to take the mass of our K atoms, which is potassium atoms, and we're going to divide that by its molar mass, which we can obtain that value using the periodic table. We find that to be 39.1, and that will give you your number of moles of potassium. And so if you're going, in this case, from your grams to moles, that is how you calculate it. So let's look at another situation. Here you have a liter of air that contains 9.2 times 10 to the negative 4 moles of argon. And so that is in moles, and then it's asking you for the mass of argon in liters. Well, previously we were given the grams and we were tasked with finding the moles. And in this case, we're being given the moles and we're tasked with finding the grams. Now to do so, you're going to take your moles of argon, and instead of dividing like we did prior, we're going to multiply by the respective molar mass of the compound. In this case, the molar mass is different because the element we're talking about is different. So you're taking your 9.2 times 10 to the negative 4, and that's going to be multiplied by a value of 39.95. And again, the 39.95 comes from the molar mass of argon, and that yields your mass of argon, which is 0.037 grams of argon. Now, here we're given a situation where we have our moles and they're asking us to convert to mass. And so they say vitamin C is a covalent compound with the molecular formula C6H88O6. The recommended daily dietary allowance of vitamin C for children aged 4 to 8 years is 1.42 times 10 to the negative 4 moles. And we're being tasked with finding the mass allowed in grams. And to do that, like we've done before in the other example, because we're going from our moles to our mass, we're going to multiply by the molar mass of the respective compound. In this case, we take our 1.42 times 10 to the negative fourth. We're going to multiply that by 176.124 grams, and that's going to yield a value of 0.0250 grams of vitamin C. So the concept here is you're multiplying. So when you're going from moles to grams, you multiply, and when you're going from grams to moles, you are dividing. Now, we're going to look at a new topic here, now that we've kind of talked about the idea of comparing using grams, moles, and atoms. Now we're going to look at the idea of balancing a chemical reaction. Now, to balance a chemical reaction, you need to understand that everything that you begin with in a chemical reaction is what you yield in a chemical reaction. And the only difference lies in the fact that the atoms themselves simply rearrange themselves just to form separate constructs. The number of featured atoms should be the same as both on the reactant and on the product side. And that's what we're going to be looking at, how to balance those relative quantities. And we're going to balance them by changing a number called a coefficient. Now, coefficient it seems like more like a math term, but it's definitely applicable when you're talking about balanced chemical equations, and we are going to adjust the coefficients of chemical formulas so that we can generate a balance in the number of atoms both on the reactants and the products. So in any chemical reaction, the substance undergoing the chemical reactions on the left-hand side is your reactants. The substance on the product side are on your right side. You have a plus sign, which indicates that you're separating individual reactants from products, and it just shows you that you have different chemical formulas. And then your arrow is kind of like a before-after, which separates your reactant and your product, and is going from left to your right. Now, as I mentioned, the relative number of each reactant and product species are going to be represented by your coefficients, and your coefficient of 1 is typically omitted. So anytime you don't have a number next to it, it's understood to be 1. And in most cases, when we're balancing reactions, we're going to be looking for reactions that feature whole number values. You want it to be whole numbers, and you want it to be the simplest whole number values. Adding to that are a few concepts or word choices that we want to be familiar with. One is gas, the other is liquid, the other is solid, and another one is aqueous. Now, when we're talking about aqueous or aqueous, we're talking about material that has been dissolved or solvated inside of some type of water-based media. So when you think of AQ, if you see it next to a compound that you know that should be solid, like NaCl, which is sodium chloride or classic table salt, it means that that table salt has been placed in solubilized in water. So in this reaction they have sodium, which is a solid, water, which is a liquid, sodium hydroxide, which is aqueous, and then hydrogen gas. Sodium hydroxide means that sodium hydroxide can be a solid, but it's been dissolved in water, and now that makes it aqueous. So it's common practice to make sure we're using the smallest whole number ratio when we're talking about balancing chemical reactions, and we reaffirm that the subscripts are your numbers that define the identity of the substance, and so we're not changing the subscripts. We're going to keep those numbers as is, but you can adjust coefficients. So let's walk through the process of understanding how one balances chemical equations. When you're balancing a chemical equation, it's customary to write down the number of starting amounts of each material, both on your reactant and on your product side. And then you want to adjust the coefficients so that your number of each respective element ends up being the same. So once you have those numbers equal to one another, the reaction is balanced. And remember, you have to balance what's on the reactant side, what's on the product side, in order for it to be a balanced equation. Now, generally, balancing equation takes a good deal of practice. You want to make sure that you are able to kind of work on balancing both the left and the right, because it is a practice-based skill set. Now, speaking of balanced chemical reactions, we need to also take the time to address the various types of chemical reactions. And there are several types, and there are some that kind of tend to share tendencies with certain types of reactions that I'll talk about as I discuss these types of chemical reactions. The first type of chemical reaction I want to address is something called a combination or synthesis reaction. And an example of a synthesis reaction, you have a situation where two materials come together and form one larger construct. In fact, the description says that it's a reaction when two or more simpler substances combine to form a more complex product. And the product formed is always a compound. In this case, they're saying they're taking hydrogen and nitrogen to form ammonia. The opposite reaction of that, if you will, or a reaction that goes in a different schematic approach, is that of a decomposition reaction. In a decomposition reaction, a single compound breaks down into two or more simpler substances. So you have a larger complex compound that breaks down into smaller products. And so combination and decomposition are pretty much opposites of one another. Moving now further, we have an example of a single replacement reaction. In a single replacement reaction, you have the replacement, usually of a metal by another metal construct, to form a new compound. In this case, you have copper, and it's being reacted with silver nitrate to yield copper nitrate and silver. And in many cases, they can represent redox reactions in which an ion in a solution is displaced or replaced via the oxidation of a metallic element. Now, in order for this reaction to occur, it must be more desirable for that one material metal to replace that of another metal, or this reaction doesn't happen. Now, let's look at an example of a double replacement. Double replacement is usually a result of two binary compounds that are reacted together to form a new set of products. In these type of reactions, they have the potential to form precipitate reactions. Now, a precipitate reaction is simply just a reaction where you're having two aqueous or two liquid-like materials that are being mixed together to form a product that has more of a solid consistency. And what happens physically is this material almost crashes out in solution. And this occurs when you have two or more reactants that are dissolved in a substance and they react to form just one of the product that is solid. And that's the precipitate. Now, a double replacement reaction is different from a single replacement in the fact that a single replacement features usually one binary compound, and a double replacement features two binary compounds that are being reacted together. Now, we take a look at a combustion reaction, and this is a very popular reaction, especially when you think about how often you start your car, because it functions off the same premise of chemistry. In a combustion reaction, it's a reaction where you're reacting hydrocarbon with an oxygen, and as a result, the product yields carbon dioxide and water as a product. This reaction is usually a reaction that kind of creates some kind of water product, and it breaks down via the presence of oxygen. Now, lastly, we have a redox reaction, and a redox reaction is one in which there is a process where oxidation occurs and reduction occurs. And we have talked about the process of oxidation and reduction in the previous presentation, so if you want more information, you're encouraged to look at that presentation. But the idea of redox reaction stems from the idea that one material goes through oxidation and one material goes through reduction. And as highlighted by the examples, here there are various representations of how a redox reaction can ensue, whether it be from a combination standpoint, or as combination, it could be decomposition perhaps. It could even allude to single replacement as an example for these reactions that can occur. Now, the cool thing, like I said, about a precipitation reaction is in the ability for the dissolved substances to form a solid product. And if you look at the image to the right, you notice that you've got kind of this yellow sedimentation that seems like it's kind of forming on the bottom. And that occurs when you mix two clear liquids or two liquids that are aqueous material and they form a solid product. Now, precipitation reactions can be termed as double replacement, double displacement, or even metathesis reactions. But essentially the concept is the same, where you're mixing two binary compounds, and in that case, you form another set of binary compounds, one of which, if it's a precipitation reaction, is a solid. And that precipitation only occurs because of rules regarding solubility. Now, solubility refers to the maximum concentration of a substance that can be achieved under specified conditions. This means that can it dissolve in a liquid medium? That's what solubility refers to. Now, substances that have a relatively large solubility are said to be soluble. And if it's insoluble or close to insoluble, these substances will generate what's called a precipitate, which we've talked about. And this is solely based on concentration and obviously can be affected by temperature. Now, substances that have low solubility are said to be insoluble. And so low solubility, insoluble forms of precipitate. When something's soluble and its large solubility is exhibited, it dissolves. Now, the next type of reaction I want to talk about is something called a neutralization reaction. And it's a very popular reaction that refers to the reaction between an acid and a base. And while the reactions of acids and bases will be addressed later on in later discussion units, it needs to be understood that this is another form of chemical reaction that occur. Now, in these type of reactions, the pillar of an acid and base reaction is that it forms a salt and a water. And a classic example is provided so that you can see a reaction where you're mixing an acid with a base to form a salt and water. And what also can be seen in this particular reaction is it mirrors that of a double replacement or a double displacement reaction. Now, oxidation and reduction reactions are reactions that we kind of talked about a little bit before. But again, redox reactions involve the transfer of electrons between reactant species to yield ionic products. That means that something has to go through a process of oxidation and something's going to have to go through a process of reduction, which when broken apart, they're called half reactions. Now, these half reactions are fused together to form one larger reaction. And it's important to note that in an oxidation reduction reaction, in the half reactions, there are certain terms that you want to be familiar with. First, you want to recognize that in the half reaction regarding the sodium atom loses electrons. If you look at the sodium atom, it also gets oxidized. And for redox reactions of this sort, oxidation equates to loss of electrons. So that's what's happening in the half reaction of sodium. It's going through oxidation, which is loss of electrons. Now, if you look at the chlorine atom, it gains electrons, and the chlorine atom gets reduced. And for redox reactions of this sort, it equates to reduction, which means the gaining of electrons. Now, there's a popular mnemonic that helps people with recognizing the difference between oxidation and reduction because it's important that you understand the concept. And that is Leo the lion goes grr. The Leo in Leo the lion goes grr refers to lose electrons oxidized, where the grr refers to gain electrons reduce, or gaining electrons reduction. And so this is a very popular strategy I've seen people use to be able to recognize the difference between oxidation and reduction. Now, as I highlighted before, in the half reaction, in order for one to happen, you have to have the other present. So it's not a redox reaction without the presence of both parties. And so what happens is recognizing that sodium, even though it goes through a process of oxidation, it functions as what we call a reducing agent, since it provides electrons for chlorine. Now, alternatively, chlorine is going to function as an oxidizing agent because it effectively removes electrons from the sodium. Remember, the chlorine goes through reduction, and because it goes through reduction, it facilitates, it acts as an oxidizing agent. It makes it possible for sodium to be oxidized. Now we're going to take a look at reaction stoichiometry. And stoichiometry can be kind of a challenging task when it comes down to chemical reactions. So you're definitely encouraged to visit the resource that's embedded in the presentation PowerPoint because it is a concept that does require a little bit of practice and it is very useful at an application. So after you've balanced a chemical reaction, once you've assigned the proper coefficients, you have quantitative relationships between the atoms that are involved in the chemical reaction. And while the balanced reaction represents the cookbook perfect recipe of a chemical reaction, just like in cooking, you may not have the exact quantities, you might have more, you might have less, the same rules apply when you're trying to apply and conduct chemical reactions. And so therefore, stoichiometry becomes key because it's used as an approach to compare relationships mathematically when it comes down to chemistry. So for example, let's just take a classic example of a recipe for making 8 pancakes. And let's say that a recipe for 8 pancakes called for 1 cup of pancake mix, 3/4 cup of milk, and 1 egg. So if the recipe was written, it'd be written as 1 cup mix plus 3/4 cups of milk plus 1 egg yields 8 pancakes. And if you were trying to make 8 pancakes, this would be the ideal scenario. But what you need to kind of be able to realize, and what you probably already realize, is that if that number varies, meaning the desired amount of pancakes that you want changes, then you're going to have to adjust your recipe accordingly. Therefore, if it increases in one value, it's going to increase proportionally to the other value. If it decreases, it's going to also decrease proportionally. And so in this example here, they're talking about, hey, let's say you have 24 pancakes that you need. So 2 dozen pancakes that you need, which sums to about 24 pancakes. Well, if you need 24 pancakes, you certainly need more than 1 egg, and you certainly need more than 3/4 cups of milk. And so when it comes down to that, that can be expressed mathematically. The way they express that mathematically is they take the units that you're starting with, and you're multiplying that by the ratio, which represents kind of the coefficient amounts of each baseline chemical reaction, meaning we know that 1 egg makes 8 pancakes. That's our baseline. That's our conversion factor, if you will. And then we're going to take that ratio and compare that to that of the 24 pancakes. And that tells us that proportionally, because we've increased from needing 8 pancakes to 24 pancakes, we've increased proportionally from needing 1 egg to now needing 3 eggs for this to happen. And the same rules apply when you're talking about applying stoichiometry to chemical reactions. And it starts with having a balanced chemical equation, which is why we kind of took the time to discuss it earlier in understanding balanced chemical equations. Now, if you understand the balanced chemical equation, it gives you the coefficients that you can use to compare. So let's look at an example here. So we're looking at the reaction between nitrogen and hydrogen, and it yields ammonia gas. Now the equation shows that ammonia molecules are produced from hydrogen molecules in a 2-to-3 ratio. So we're saying that for every amount of your ammonia that's produced, for every 2 molecules of your ammonia you're producing, you're needing 3 hydrogen molecules. And so they're saying that, what if you're trying to find out how many units of everything else you need? Well, comparatively, you can do that. And so that's what the conversion factor allows us to do. The ratio of things allows us to do. So comparing them becomes a lot more easier based on understanding those concepts. So let's use that approach to solve this question here, where we're trying to convert mole to mole stoichiometry. Now we've talked about the mole concept, and so we know mole represents a quantity of substance. And now we're going to use that concept to compare amongst these compounds. They say that we're starting with 0.429 moles of aluminum, and we're looking to obtain the moles of iodine. So to do that, you need to know the moles that you begin with, which is 0.429 moles, and we're going to compare that to the stoichiometric factor, or the conversion factor that we've used to compare these two. Now we know that comparing iodine and aluminum, you get the value of 3 from this iodine here, and you get the 2 here from your aluminum. And the aluminum goes on bottom because you started with a known amount of aluminum of 0.429 moles of aluminum. So you take the 0.429 moles of aluminum, you divide that by 2, and you multiply by 3, and that gives you the relative value of your iodine. So that's 0.644. So in each case, to do a mole to mole stoichiometry, you need to know your given mole amount, and you need to know your stoichiometric factor, your conversion factor, if you will, which in this case was a comparison between iodine and aluminum. Now in this example, it's a little bit more involved because you're comparing mass to mass using stoichiometry. In this case, they're saying what mass of sodium hydroxide, NaOH, would be required to produce 16 grams of the antacid milk of magnesium hydroxide by the following reaction. So they're saying, how much of this sodium hydroxide do you need to make 16 grams of this? Well, mathematically, you start with your 16 grams, and the first step is to convert that number to moles, because moles is your basis of comparison, or your SI unit of an amount of substance. Then once they divide this 16 grams by 58.3, they get moles, and then they're going to multiply that by the stoichiometric factor, or the conversion factor, which in this case is 2 to 1 from our balanced reaction. Remember, in the balanced reaction, there was 1 mole of magnesium hydroxide and 2 moles of sodium hydroxide. And so that's where these values for your stoichiometric factors get. Now, the last thing they do is they multiply by the molar mass of sodium hydroxide, which can be obtained by using the periodic table to add up. Sodium is 22.99, oxygen is 16 or 15.99, and hydrogen is 1.01, and that's what yields 14 grams per mole. And so you multiply the 40, the 2, and the 16, and you divide that by your 58.3, 1, and 1, and you yield a value of 22 grams, which means that you need 22 grams of your sodium hydroxide to yield 16 grams of your magnesium hydroxide. Now, both examples illustrate just a few instances of reaction stoichiometry calculations, but there are various types of ways to solving it. The main focus are the two that I've shared, which are mole to mole and mass to mass, and all of the calculations are essential when doing chemistry. And so when it comes down to being able to calculate that, here is just kind of a graphical flowchart representation of how one can connect the dots between the two of them. If you're converting directly between moles of one to moles of the other, you just need your stoichiometric factor. If you're starting with, the mass of a substance, you have to take the mass and find the moles using the molar mass and then the stoichiometric factor and go from there. So this chart may be useful, but it's important more than anything to practice a series of doing these problems. And with all of that being said, this culminates our presentation on chemical reactions.